talk, the emphasis will be on the water waves, and the theory will come in where it does, but I'm going to try to hide it as best I can. So you don't actually have to understand much mathematics to understand everything I'm going to say. Okay, so the talk's in a few parts. And the first 15 or 20 minutes are just about what are the basics of tsunami dynamics. And they're pretty easy to understand, actually. So after 15 minutes, you'll know a lot about tsunamis. Then I'll talk about some mathematical issues and various theories which are used to predict tsunamis, including soliton theory, and then how they work and how they don't work. And then the last point is, well, around the world, a whole lot of people know more about tsunamis than they did 10 years ago because of these two tsunamis that one killed 200,000 people or more, and one of them killed another 15,000, and it had this nuclear accident, and we're still going to find out how many people that will eventually kill. So how do you protect people and property is the last point I'll discuss. A lot of this work is in a paper with Diego Arcas. Diego Arcas works at the, I forgot the name of the thing, it's the United States lab that predicts tsunamis. So it's the official predicting thing for, pardon? Well, it's within NOAA, though. It has another name.
It's PMEL, P-M-E-L?
Yeah, Pacific Marine Eggplant and Lasagna.
Yes. But it's in Seattle.
Yeah, it's in
Yes.
Seattle, yes,
You
yes.
realize you are on air when you
Okay. Okay, so let me give you the big picture first. There's a video taken of this town called Tsunami in Japan, and it lasts for about 5 minutes, and you can see what happens to the town of Tsunami over the first 5 minutes. You'll see what an actual tsunami looks like in real life. So let's see how that works. I want to go, how do I quit this? Nope, I don't want to do that. Do that. And then I want to go here.
That's on a slightly bigger scale.
Whoops, it's supposed to. There we go. Whoops. What happened?
Display mirroring, it's at night. Tsunami is moving.
I can never keep my eyes open underwater.
So how do we do this? It's showing up here.
Oh, is there on?
You got a mirror, maybe this.
Yeah.
Where's display? Let's see.
Here we go.
You got it?
No.
There's a way. Arrangement.
Yeah,
Mirror display. There we go. I think now whatever you do, now it looks kind of goofy here, but at least you'll be able to.
Okay, so let's try again. Full screen. Okay, so a tsunami is a very long wave. If you think of a wave ought to be something like a sinusoid, then I'm going to show you 5 minutes, and the water level is just coming up. So it's this part of the wave, and then the period of the wave is something like 20 minutes or something like that. If you've been does anybody here a surfer? Okay, so a 10-second wave is a pretty long wave. 20-second wave is very long. This is 20 minutes at least. So tsunamis are the longest waves that live on the ocean surface except for tides. It's very long. And the other thing you'll see, you can see in this picture already, if you look across, it's flat. So you don't see any spatial variation at all.
Those are mountains in the background, by the way. That's not a wave.
Right, right. Okay, so let's do this.
Hills.
What happened to the sound? Okay, well, you know.
Oh, yeah, on the left.
Pardon?
Down from your cursor 1 inch
On
or
the left
foot.
bottom, you have to do
The
the
left
plus
bottom.
thing.
Here? Oh, there. I see.
You have to move the circle.
You have to move the circle. Yeah.
Oh, I see. Okay. So that's a warehouse. You should look at the whole picture when you can, because the whole town is going to disappear except for two buildings. The one where the guy is taking the video, and another one which is right around the corner here. If anybody has questions while this is running, feel free to ask them.
How do you pick the building to stand on?
Pardon?
He's very lucky to have picked the one building that's not gonna go away.
Well, or
That can be correlated with,
Yeah.
Emmerich existing.
Oh, no.
Because
it's
other
the only
building-
video that's left. It's more like-
The anthropomorphic principle of Tsunami.
Yes.
How do I get rid of this thing down here? No? Darn it. Come on. There you go.
Do you know how far it is from where he's filming to the ocean?
Oh, it's right around the corner.
Right around the corner?
This is a port town. That's why the warehouse is there.
Boat moving.
That's the best thing to do is get away. Stay away from the land.
Actually, if you're interested in tsunami, they made a film about the 2005 tsunami. I don't know if you've seen that. And it's actually based on a true story. The English family.
Oh, I know about that
Oh, you
story.
saw that?
Yeah.
Did you see the film?
No, but
The
I,
actual tsunami effects is absolutely fantastic.
so that's that warehouse that you saw sitting there.
Did the citizens didn't get any warning? They didn't?
You heard a siren going at the beginning?
Oh, yeah.
That's so late.
Well, it might have been going for maybe 4 or 5 minutes, right?
I don't know. I mean, I don't know how long it was going before this guy started recording.
This
That's a
was
bit late.
This was very close to the epic center of the earthquake, right?
Pretty
So
close,
it
yeah.
was just 5 minutes or so.
Yeah, yeah. Remember that town that used to be there?
What was this other reflection?
Pardon? Oh, that's like a hydraulic jump, yeah. At least that's the way I interpret it. This is the top of the building where the guy is taking the video.
He's going all right now. He can stop rising right in the water.
How high did you begin?
I'll come to that in just a minute. 8 or 9 meters up.
Building minus 4 foot.
Well, if you look at the other building, it's the water's now up to the window on the second floor, and it goes up to the top of the window before this video stops.
Is that a boat?
No, that's the roof of that warehouse.
Roof of the warehouse. Oh, wow.
We have a feeling is the water level still rising at this point.
Yeah,
It is.
yeah.
Okay, except from the one.
And going out is also destructive.
Yeah, the water's up, almost up to the top of the second floor windows now.
There are people on that balcony.
Yes. In fact, there's another guy up there taking another video. I found that out just recently. Okay, let me stop it there. How do I stop? Okay. So, there's no sign that says.
Push this, yeah.
There we go, okay. And then I go get rid of all this stuff. Let me go back one. No, okay. So that's what a tsunami looks like if you're standing right at the spot and you're not drowning. The basis of the tsunamis is these tectonic plates that we all have learned about, and one of them sliding underneath another one. And well, what earthquakes come when plates move relative to each other, and tsunamis come when one of them slides beneath another one, and you're on the edge of water. So this is an official NOAA map, And all the red lines are where one plate is sliding beneath another one. So those are all the places where tsunamis can come from. It's not true that all tsunamis are generated this way, but a large fraction of them are. So the 2004 tsunami started right there. 2011 earthquake on the edge of Japan started there. The biggest earthquake ever recorded was in Chile, starts there. So those are the places where the earthquake is likely to start. And the reason that they're well documented by NOAA is so they can put their instruments so as to catch as many of those as possible, as soon as possible. And the mechanism is there. I'll show you with my hands what's going on. Here's a plate, and here's another plate, and this guy's sliding underneath that plate. So for the 2004 tsunami, India is sliding beneath the Burma plate. It's
The
also
other way that you'll match the board.
okay. So India is sliding beneath Burma and slides like that. And for the 2011 earthquake, it's the Pacific plate is sliding beneath Japan. But it's the same mechanism in both cases. And what happens is the sliding is going on for centuries. And then at some point, something gets caught. And then when it gets caught, the sliding continues and the upper plate bends. And the lower plate also bends, but the upper plate that matters. So that happens over decades and then snaps. So the bending happens over decades and the snap happens over seconds. And when it snaps, this part of the plate goes down and that part of the plate goes up. Goes like that. So what happens in the 2004 tsunami in Indian Ocean, a positive wave was on the outside part and a negative wave was on the inside part. And then the inside part goes to the land nearby. And you may have heard from people that if there's a negative wave, you should run away as fast as possible. That's because it's usually a negative wave that comes back towards the nearest land. So just get out of there as quickly as you can. In the 2011 earthquake, the part that came down was actually on land. So part of Japan is now lower and further east than it used to be because of that earthquake. Okay, so here is the beginning of a video of how this whole thing worked by Sataka. There are a lot of other people who have done the same thing. Ward is one, but I'm keeping Sataka's video because he put it up like 2 or 3 days after the tsunami, and he didn't have to change anything after that. So that's impressive, I think. Well, yeah, so the red part is the part of the water that was raised, and the lower part is the part that was lowered. The blue part is the part that was lowered. And the boundary between those two plates is right along here, and there's an island there, and there's an island there, and there's an island there. Those islands are called the Nicobar Islands and the Andaman Islands, and they mark the boundary between these two plates. So that's where the earthquake actually occurred. You can remember back to 2004, there was a town called Bande Aceh. Remember hearing about that? That place was right here. And the earthquake was 250 kilometers away from it. And the thing that was unusual about this earthquake, it was pretty big, but the main thing, there was an earthquake here, and then that relieved the stress there and increased the stress up here. Then there was a second earthquake, and then that did the same thing, and it regenerated a third earthquake. It's like taking a piece of paper and just tearing it, is what happened. And the earthquake propagated along here, a series of them. And up here it says we're starting at 10 minutes. And the reason is because it took 10 minutes for the earthquakes to stop. So who's ever been in an earthquake? Anybody? So some of you. And it's small one, okay. But it feels like forever, and it's really like a few, some seconds. Yeah. So imagine 10 minutes of this earthquake going on and on and on and on. And the people in Bande Aceh felt the first earthquake because it was nearby, and then another one, and another one, and another one. And after 10 minutes, they said, I think I'm still alive. And then about that time, the tsunami came in and wiped out everything that wasn't already destroyed. So, whoops, this way. Yeah, so in the 2011 tsunami, The earthquake was not 250 kilometers away, it was 70 kilometers away. And a 400 stretch of coastline dropped more than half a meter because of that earthquake. And it moved Japan 2.5 meters to the east, the chunk of Japan. This graph I just found out about recently. It was published in Geophysical Review Letters 2 years after the, well, 1 year after the tsunami. They took that video that I just showed you and another video taken by a guy in that other thing. They put them together, and then they just studied the video and did various things, tricks with it, and they could figure out what was the water, what happened with the water. And it just went up and up and up and up and up. So there's 9 meters above the usual level. And I don't understand this first part because it says it started at 3 meters below where it should have been, but this other thing said it drops 0.6 meters. So I don't know what to do with that. Anyway, the drop, I mean, the growth went on for 20 minutes, and then it started to come back down. And the other thing they did was they could figure out from this and from again, staring at the video, how fast things were moving, and they got currents that went up to 11 meters per second of the water. And then in the article it says, if you had a boat, you would not be able to navigate it in that strong of a current. Okay. All right. So these are the equations of water waves, and most of you will say, oh yes, those are the equations of water waves. And for the people who don't know water waves, take my word for it, those are the equations of water waves. Almost everything I'm going to say has to do with approximations to this. So we're going to, those are in the background, but don't worry about them if you don't know what they mean.
Nor the fish.
Right. Yeah. So I think everybody knows most of this. Sound waves are what you're hearing now, and there's a speed of sound. And water waves are dispersive, which means for gravity waves, the longer waves travel faster than the short waves. And that's true. You're going to hear, those of you in this conference, you can hear about that over and over and over again this week. But there's this, well, let me skip that. There's a limit for very long waves. The speed of propagation, according to linear theory, is you take the depth of the water wherever you are, multiply by gravity, take the square root. And then that gives you the speed of propagation of the tsunami. So tsunamis are very long waves, so you can expect them to be going at that speed. And d changes with where you are, so the waves can speed up or slow down depending on where the waves are propagating over. So let's go back here. There are some relevant length scales. Again, the red part is what's going up, and the blue part is what's going down. And I'm going to claim that the wave amplitude is actually quite small. We're really talking about linear theory for most of the propagation time, and they're all going at that one speed. So if you think about the one-dimensional wave equation, everybody who's taken a PDE course anywhere has learned how to solve the one-dimensional wave equation. You take the initial signal here, the positive part there and the negative part there, split it in half, send half of it that way, and spend half of it that way. So the people in India felt a positive wave followed by a negative wave. The people in Thailand felt a negative wave followed by a positive wave. Okay. Let me give you some scales. The Bay of Bengal is the part between where that red spot was and India, and the depth is something like 3 kilometers. It varies depending on where you are, but 3 kilometers is a good number. Andaman Sea is like a 1 kilometer. The wavelength, the direction of propagation, is the width of that red spot, or the width of the blue spot, and it's something like 100 kilometers across. So if somebody wants to argue and say it was 50 kilometers or 200 kilometers, that's fine with me. This is an order of magnitude thing. The wave amplitude is 1 or 2 meters, and the distance along that curve is 1,000 kilometers. So the speed of propagation across the Bay of Bengal is 600 kilometers per hour, and across the Andaman Sea is smaller than that. So I flew here yesterday on a big jet, and it goes faster than 620 kilometers per hour. But if you want to go take a medium-sized plane and go from London to Amsterdam, then typically that's the kind of speed a medium-sized airplane goes. Okay. So it's pretty fast. Okay, so here is animation. see the red wave goes first and gets to the other shore. If you look at the other side, I can do it again. Blue wave goes first and reaches Thailand. The time is about the 2 hours for both of them. So the wave over here was traveling faster and the distance is longer, and the wave here was going slower and the distance is shorter, and it works out that they both got to shore about the same time. So, linear wave equation, what's so big about that? How can these waves be so complicated if it's such a simple model? Question. So let's walk through that. Imagine you're a fisherman and you went out fishing in the Indian Ocean on December 26, 2004. So here's this wall of water. It's a meter high, it's 100 kilometers long, it's 1,000 kilometers in the other direction, and it's coming at you at 600 kilometers per hour. That sounds fairly scary. Let's see, I want to go here. So the speed, again, is square root of GD, and it's moving towards you. So this is what I just said. It's going to go at that speed, but what do you see? The wave is 100 kilometers long, so it's a sixth of 600 kilometers in an hour, so it takes 10 minutes for this wave to go by you. So you're in your boat, and in the course of 10 minutes, your boat goes up by a meter, and then it goes back down by a meter, and unless you're very sensitive, you probably wouldn't even know it happened. So away from shore, tsunamis are not dangerous at all. When it comes in close to shore, then everything changes. The speed is still this, but the depth is getting smaller. So as it comes towards shore, the wave slows down. And the more accurate statement is the front of the wave slows down. The back of the wave is still 100 kilometers out at sea, so it's not slowing down. So the whole wave compresses as you get in close to shore. And it compresses this way, but water is pretty incompressible. If you've ever dived off a diving board and landed the wrong way, you know what incompressible means. So if it squeezes in this way, it has to rise up that way. And then that's why this thing is so dangerous, because a wave which was 1 meter high in the open ocean becomes a lot bigger near shore. So all the destruction happens near shore, not away from shore. And then what happens near shore is well, there's a lot going on back there. Okay. So based on the scales that I showed you, the wave amplitude is a meter, and the ocean depth there is 3,000 meters. So that's a pretty small number. That's why you can linearize the problem, away from shore anyway. There's one speed of propagation, and the speed of propagation is this thing right here. If you go get a map of the world's oceans and just measure, you can figure, it's recorded what the depths are all over the place. So you can predict easily how long will it take a wave to get from this spot to that spot. That part is not hard at all. The people who do the official prediction use hyperbolic equations, shallow water equations instead, but you're going to get almost the same answer as this, because the change in depth, if the wave changes from 1 meter high to 30 meters high, you're still talking about 30 meters in a sea of 3,000 meters. So it's just, linear theory will do fine in terms of getting you from the source to a nearby spot. A spot. But what happens near shore is a different issue. Okay. So once we get to shore, a lot of things happen. Nonlinear effects, wave breaking. The topography matters a whole lot near shore. And I used to have a slide right here which told me about that. I'll come back to that, I guess. Okay, so I'll show you a slide showing how much variation there is along the coastline in Japan, but it's not here where I thought it was going to be. So what are the theories that you use? This is a picture of the Korteweg and de Vries equation. I've seen a picture of that somebody has told me is a picture of de Vries, but I don't have it here. They invented their theory to describe the motion of moderate waves of long amplitude in shallow water. That sounds like what I've been telling you about, right? So this ought to be great. The question is, how well does this KdV equation work for predicting tsunamis? So if you've never derived either the Korteweg-de-Vries equation or the Knapsack-Petfius-Philly equation, which is a two-dimensional generalization of the KdV equation, there's 4 length scales and they fit together in a particular way in order to justify getting the KdV equation. So the first assumption is you have long waves. So the wavelength in the direction of propagation is a lot longer than the depth. So for the 2004 tsunami, I gave you the number 100 kilometers this way and 3 kilometers this way. So that's 1 over 30 or so. You're supposed to square that so you get 1 over 1,000 more or less as your small parameter for long waves. And they should have small amplitude, and that's 1 meter divided by 3,000 meters. So again, that's also a small number. That sounds pretty good. The waves are supposed to be moving approximately in one direction. And then if you have that exactly, you'll get the Korteweg-de-Vries equation. If you have it approximately, you'll get the KP equation. And then all of these small effects should come in the same order in order to get KdV to work. Okay? So take those approximations, go back to the equations of water waves, put them in, turn the crank, and out comes a leading order. Whoops, I went the wrong way. What happened here? Whoops. Oh, I just gave you those scales again. Okay, I see. So amplitude over depth is 10 to the minus 3. Depth over wavelength squared is 10 to the minus 3. The aspect ratio is 10 to the minus 1. So it's not as small as the other two, but that's the way it is. So put those into the equations and turn the crank. And the leading order, you'll get the wave equation with this speed. So you have a wave going to the left, you have a wave going to the right. That's all the wave equation has to say to you. There's nothing else to talk about after that. If you follow one of those waves, like this one, and you get an coordinate system moving with the speed square root of GD, then at next order you'll get a small bit of nonlinearity, which you swept under the rug at leading order. It comes back at the next order. And a small bit of dispersion for the same reason. And if you're in two-dimensional surface, you'll get a small bit of two-dimensionality coming in. So that's where those equations come from. Okay. So everything looks pretty good for KdV, right? We have small amplitude, we have long waves, we have nearly one-dimensional wave. And the other thing you need is you need a long distance. So if the wavelength is 100 kilometers and epsilon is 1 over 1,000, then you need 100,000 kilometers before you'll see KdV dynamics. So the distance across the Bay of Bengal is 1 kilometer, not 100,000. Distance around the world is 40,000 kilometers. So it's a great theory, but it really doesn't have much to do with tsunami propagation. Okay. So the next model is what are called the shallow water equations. That name is sort of presumptuous to me because there's a lot of things which describe shallow water equations, and this is one of the theories. So why does it have the right to use that name? I don't know, it does. You start with Euler's equations, and instead of you assume long waves again, but instead of
called the shallowest.
right. So you start with Euler's equations, assume long waves, but don't necessarily assume small amplitude. So the amplitude can be as big as it wants for shallow water equations. And then you put that in and you get two basic principles coming out. If you assume hydrostatic pressure, means here's the top of the water, here's the bottom of the water, you're right here. Just measure the distance to the top and see what's the weight of the water sitting above you. That's what defines the pressure. That simplifies the equations a lot. And the other thing is, in the other two momentum equations, you skip the vertical accelerations. And if you make those two assumptions, then don't get that equation. Where are we? Yeah, that's where I want to be. Okay. So these are the equations. H is now the surface elevation, which changes with time, plus the distance all the way down to the bottom. So it's the total water column is the variable H. And the top equation says mass is conserved, and the bottom two equations are the momentum equations. The right-hand side of these are known, and everything else you're solving for. So those are the shallow water equations. Okay. So then the question is, okay, well, I know what those equations are. How well do they describe what happens in shallow water? So here's where Joe Hammack comes in. I met Joe Hammack when he was a graduate student and I was a postdoc about 1,000 years ago. I met him in the parking lot of the apartment complex that where we both had apartments. That's how I met him. He told me about what he was doing for his thesis, and he was working in civil engineering, and he was doing a thesis on generation and propagation of tsunamis. I said, oh, I was learning about the quarter-Wave equation at the same time. I said, oh, I happen to have an equation in my back pocket. We ought to see how these fit together. So here's his tank. Imagine a long tank, and then he would put in like 5 centimeters or 10 centimeters of water, and then down at one end of the tank, he has a piston. And the piston can go up, the piston can come down, you can shake it, you can do anything you want to with it. That's supposed to represent the seismic contribution. So if he pushes it up in a hurry, then the water just moves up above it, and then it falls down. And that creates a tsunami propagating away from the paddle. If he pulls it down, you get a negative wave, there's a hole in the water, and again, a wave propagates along. So let me show you 2 sets of his data. He did positive waves and he did negative waves. I'm going to talk about the negative waves right now. So here's one experiment. Here's another experiment. These things are equal distance apart down the tank. The time variable in Korteweg-de-Vries equation is actually distance down the tank. And the initial time, if he pushes the piston down fast enough, there's a box that gets created. And so the shape of the initial wave is a box, pretty much that. And then as the wave propagates, it changes its form, and these short wavelength waves fall behind. So the longest waves are traveling the fastest because the waves are dispersive, and then you're in the coordinate system here where you're traveling with the speed square root of gh. GD is what I have been saying up until now. If you look at the front part, the volume of water that's displaced is pretty much all there. And you can't tell it from where you're sitting, but if you had a ruler and you put a ruler on that line right there, it's pretty much a straight line. If you look at take the Korteweg-de-Vries equation, there's a solution which is U is constant times x over t. That's what that thing is. So there's a slope given by x over t, and as time goes on, t gets bigger, and so the slope gets smaller, and that's what you're seeing in the front of the wave. Okay. Over here is another experiment. Everything in this experiment is the same as it was there, and the single difference is the wave amplitude is bigger. We pull the piston further down, and over here you see the biggest wave amplitude is like 0.07, and here 0.07 is way up here. So this wave amplitude is larger. And the consequence of that is there's a lot more energy in these oscillatory waves than there was in those waves. Both of them have oscillatory wave behind the leading wave, but this one has a lot bigger one. Okay. These are called dispersive shocks. Dispersive shocks are becoming fashionable. They're not the same as viscous shocks. Viscous shock would just say you're at this density and then jump up to that density and then life goes on. But that's not what happens here. Instead, you get these oscillatory waves. So now I'm going to show you some photographs taken near the edge of Thailand. And I'll tell you what I see. I'm going to tell you I see this picture. But the photographs are the photographs, and you can decide what you think you see. So these were taken by this guy, Anders Grauen, who is from somewhere in Scandinavia. We tried to contact him and failed to do so. So I don't know the guy. If he walked in now, I wouldn't know who he is. But here's a picture he took from the top of an island. And if you wanted to go lie on a beach, you see here, there's a light-colored sand and then dark-colored sand. The light-colored sand is what you would have called a beach. And then this negative wave came in, and all the water went running out to sea. So that's what the dark-colored sand is. It's the water. It's the sand that used to be underwater. And then this part is very flat. The surface is very flat. I mean, in the picture, it looked like it was on a slope like that, but that's because we squished the thing down in order to get everything in. If you look at it on a real scale, it looks almost flat. And then there are these oscillatory waves behind it. And the biggest one is the one in front, and it's breaking. And over here, you see almost the same thing. He took this looking in some other direction. This again has, you see no ripples at all here, followed by 1, 2, 3 breaking waves, followed by a whole bunch of other waves behind it. I think it's the same picture that you just saw. Okay. Here's another set of photographs taken by somebody else, again on the coast of Thailand. This part here is this part before the wave comes in. So it's very flat, and this all used to be underwater. And then out there, you see this very long crested wave where the wave's breaking. And when it gets in closer to shore, you can see there's a wave breaking here, and then there's two boats, and then there's a second wave. So the first wave is big enough to break. The second wave is also big enough to break. It's possible the third wave is also breaking, but I can't see it anymore. Okay. So it's the same picture. If I go back to slides, whoops, that's 3 slides. The biggest wave is in front here, and it's not so obvious here. It's obvious there, the biggest wave in front, but further down you go, the less clear that is. But for short distances, the biggest wave is going to be in the first one. Okay. So that's what I'm claiming. This is the process that happens for negative waves propagating in towards shore. And the question is, who actually cares? Yes, they're different, but does that matter? And the answer is, for any of these theories for long waves, if you say I'm going to take only waves going in one direction, then the water velocity in a horizontal direction is proportional to the wave amplitude. So the measurements here are measuring wave height, but you can also translate them into horizontal velocity. And then,
You just said a while ago that it took 100,000 kilometers for KDV to work. And it's KDV that would give you dispersive shock.
KDV is a thing that will give you a dispersive shock.
So you're saying now that you've got to add, but shallow water won't give you this.
Right. Shallow water will not, because you made the equation hyperbolic like they weren't originally. Yeah, there's no dispersion in them. So I'm going to come to that in one second.
So what was the comment about the KDV not being valid? I didn't make the connection there.
Oh, okay. So if you want to see soliton dynamics, for example, you'd have to wait a long time.
Yeah.
But this process doesn't take that long. So so Paul is right that the KDV theory will predict this, but if you didn't have KDV theory, you could also try to predict this.
So how did you find that it takes too long for the KDV? What was the argument again?
Oh, so you need a distance which is 1 over epsilon of a typical wavelength. So if a typical wavelength is 100 kilometers, and the small parameter is 1 over 1,000, then you need 1,000 times 100 kilometers.
What measures the small parameter?
Two different things. One of them was amplitude divided by depth. And
So you have a measure of epsilon.
yeah, well, that's one of them.
And the time is like 1 over epsilon cubed, I guess. That's what you're.
No, it's 1 over epsilon. But I get a time scale of order 1. I can define the time scale of order 1 to be the time it takes a wave traveling at speed square root of GD to go the distance of a wavelength. That gives me my order 1 time scale, and then my slow time scale is 1 over epsilon times that.
It's 1 over epsilon cubed.
So if you scale things the way you want to, then the leading order thing is epsilon to the 1/2, and the next thing that comes in is epsilon to the 3/2, and then that's where you're.
That's how you define epsilon.
Yes.
Yeah, right, okay. All right, so as one of these people just said, shallow water equations don't have this in, and you can think of this as horizontal velocity going back and forth. So imagine that you're deciding you want to get out of here, and I want to go build myself a beach house someplace warm where I can lie out on the beach and do nothing. So you build this beach house, and then if you get this, it's like putting your beach house in a washing machine, because the waves are going back and forth like this all over again. So it's much more, this is going to be much more destructive than just a single wave coming through. So then the question is, how do these different theories compare? This is Joe's data again, and the blue curve here is that data digitized by hand by Joe Hammock's son Knox. Actually, he put in the dots. So the blue line is supposed to be exactly what you see over here, and then the green line is what the shallow water equations predict. They predict a viscous shock right there, and then flat after that. So the shallow water equations get the leading part pretty much correct, and everything after this is all wrong.
Harvey, why do you call it a viscous shock? Isn't there no viscosity in the shallow water equations?
No, nobody.
So yeah,
It's like the weak limit or something?
yeah, it's right. If you do the gas dynamics, then you get shocks, and the shocks are due to
But
viscosity.
it's just the hydraulic jump is what you're putting there, right? It's
Yeah,
not
yeah.
in that
It's
viscosity
just a
shallow water.
discontinuity.
The hydraulic
Yeah.
jump is a viscous shock.
Yeah. So it was a misnomer. I apologize. I take it back. It's that kind of just jump in the height. Okay. So all of this stuff is not predicted by shallow water equations. And if you're in the business of predicting tsunamis, knowing how long it takes to get there is easy to do. People what really want to know is, am I going to die if I stay here? Is my house going to get washed away if I don't stay here? What happens near shore is very relevant. And if you're missing all this stuff, then you're asking for not a very good prediction. So the first I should say, this is David George, who did his thesis at the University of Washington, and his thesis was on building a shallow water model. So that's his model work there. John Carter is also in Seattle. And again, the blue curve here is the data from over there. The green curve is what the Korteweg-de-Vries equation predicts, and the black curve is what the Whittam theory predicts. Whittam theory being ut plus uux plus an integral term with a dispersion relation built into the integral term.
That's normally called the Whittam equation.
That's what it says there. Whittam.
You said Whittam theory.
Oh, I see. All right. So either one of these models does better than the shallow water equations in predicting what happens here. But one other thing you see is not only are you getting all these oscillations, but the amplitude is still wrong. So in addition to putting in dispersion, it's also necessary to put in dissipation. If you think about doing boundary layer theory in gas dynamics, one thing you can do is you have this Manning friction coefficient, which tells you about how much roughness there is. Think about the video you just saw. A car is like a grain of sand in that picture. So there's a lot of stuff that'll slow down the water once you come on shore because of all those buildings and cars and all that stuff, trees. Okay, here's the figure I wanted to show you earlier. This is local variation in topography. So run-up is how high did the water go before it started back down again. And then these are recorded values for how high the water went in different places. This is 10 kilometers across there. So look right here. All of those places are a few meters apart because it's certainly not more than a kilometer from anyone among any of those guys right there. But the amount of run-up is like 18 meters here and it's 40 meters there. So huge variations in what happens when you come in toward shore because of these little variations in the bottom topography. Okay. So the last question is, what do we do to protect people from tsunamis? Okay, and I'll give you two things to think about. In my opinion, the most important issue is zoning. So for the, what's the name of the name of the nuclear power plant was at Fukushima, yes. So here's the water, and then here's land sloping up slightly, and the power plant was built right on the edge of the water, and then there's a steep rise after that. And this is a stone tablet that's sitting up on this part of the ridge, and there's a sequence of them all along here. And it says in ancient Japanese, high dwelling places, high dwellings are the peace and harmony of our descendants. Remember the great calamity, because the calamity of the great tsunami. Do not build any homes below this point. Zoning ordinance from 700 years ago. And they didn't have it at the time, but they probably put in an asterisk after this. And by the way, don't put in any nuclear power plants either. You just don't want to be there. That's the most important point.
Have they now put new stones at the?
I don't know. I don't know.
Did that stone get wet?
No. I mean, it's pretty high. So vertical evacuation centers are the other thing that are relevant. Those two reinforced concrete buildings you saw in the video, the one where the guy was taking the picture and the one you could see, by the end of the video, they were both still there. And almost nothing else was still there. That's what's meant by a vertical evacuation center. Go to some place where you can go up. And then if you get up high enough, then you won't die. At least not during this tsunami. But Harry Ye, who works in this stuff, told me that there's some place or other where they built one of these, and they didn't build it quite high enough. So a lot of people went there and they went up on the roof, and then the water came up above the highest point, and then it didn't help you be there at all. But
So I have a question for the room.
Yeah.
Which is, you could also imagine a subterranean evacuation center, just with doors which would close solidly.
solidly,
And solidly, or they can leak a little bit, but just not too much. That will last 20 minutes, right? And that could be like a parking structure.
that's,
It's
well,
very hard to build something, however, how high is it? 40 meters high?
With the
It
water
sits there.
stage,
No.
the water stage, partly.
Sorry?
It takes a while for the water to.
It takes a long time to.
Well,
need to
40
receive.
minutes. 40
The
minutes.
water to receive, yes.
But not
And there are several ways.
Yeah.
That's just in local convergence. That's where the water can go away. That's why where it went up so high in valley.
We
So
just
you
have to
should-
know, you just have to know where it's going to focus.
Yeah. But when you're in the valley, that's where it came from.
Yeah, but I'm just, it's not completely out of the question. I was just.
I think there's an element of psychology that's really hard to tell people that there's a
Yes.
tsunami and go on the ground.
I agree, but it's easier to build a parking structure underground with solid doors than a huge platform 40 meters in the air.
I'm not sure that's
If it's
true.
If you have an open field, you don't need to go 40 meters, because the 40 meters only happens when you have convergence. So when it's open area, you probably 10 or 15 meters higher.
Well, all of Tsunami had to have a platform, a big platform.
Now, but it didn't go up 40 meters in Kissimmee.
Right,
It was
right.
about
But-
10, right?
Yeah, that's
but,
true.
well, digging costs a lot more than building up.
Yeah.
Anyway, that's the end of the story.
Wow.
Questions? Comments?
I have a question.
Yep.
So I remember hearing a talk, someone, not you, talking about modeling of tsunamis, and it seemed like the state of the art at that time was when you model the very initiation of the tsunami, that you just take the shape of the dislocation at the bottom, and then you just move it to the top, and that's your new resurface with no velocity? Is that still state of the art, or?
There are two issues that the tsunami people have trouble with. One of them is there is a tsunami, there is an earthquake, and I have a very limited time to translate that into a warning system. And if I have a measuring device that happens to be where the earthquake was, and it probably got washed out by the earthquake. So then you have to think about that. So they don't have very good ways of getting the initial data. That's point number one. And point number two is when it comes to close to shore, then they have to do something to model. There's a house here, and there's a house here, and there's a big building there, and that's all over. So those are the two things that they need. Yeah.
Is it just to follow up? I understood, but please correct me, that actually the tsunami warnings are actually tabulated, so they don't do the whole calculation. They have a scenario of calculation, so then they have them instantly. So they have to assess which scenario or which set of scenarios is relevant, and then those are pre-calculations. Just
Yeah,
to give some background. So they don't do the calculation online because it's too slow. They actually try to guess and get a better guess to see which scenario or which set of scenarios applies.
Mhm.
Because I think they do both. So there's a lot of stuff that's pre-calculated,
Yes.
and then for, especially relevant for nearby.
Yeah,
sites.
for the nearby, exactly. And then
Well,
when they have
But
time,
there's
they
also online
calculate. Yeah.
computation that, and there's definitely a lot of after the fact
Oh, definitely.
computation to calibrate and to fix and to.
And to get a new, better
Right.
scenario, set of scenarios available. Yeah.
Mhm.
Your first slide mentioned improving aggression models.
Yeah.
So these models are they based on shallow water equations? So your findings suggest that we should
Including dispersion.
all include
Yeah, yeah.
dispersion.
Near shore, you need to talk about dispersion at least, and you need to talk about dissipation both. And my opinion is that they're not doing the initial value problem correctly. And I tried to, one of the reasons I wanted to work with Diego Arcas was because he worked there and I could find out exactly what they do. He got in trouble for the paper we put out because it suggested there might be some shortcomings of their model. So, so then he said, I can't work with you any longer.
Oh, really?
Yeah.
So usual comparison of shallow water, KDV, and
Whittam.
Whittam equation. But both KDV and Whittam are small amplitude equations. Shallow water is arbitrary amplitude. So there is a Serre equation, or Sugardner, or Kamasa, or what's it called? Green-Nagdi,
Yeah.
which is sort of how to add dispersion to shallow water, right? Full amplitude.
That works too.
You didn't try, but that graph wasn't there. Does that graph make a difference?
John did 3 different models, and then he had 3 different graphs with 2 of the models at a time. And so I left one out to give you a picture, and I forgot which one I left out, but it could have been a Serre model.
Okay.
Is it Serre?
But it wasn't any better.
Yeah, it's pretty much the same. The biggest shortcoming of all of them at
Is
this point is
dissipation.
there's no dissipation, yeah.
One wants to predict also the runout.
Yes.
How can you predict that? Is it possible to, within these models, to predict runout or not?
Yeah, it is possible. I mean, it's easy to make a prediction. The question is, are the predictions anywhere close to accurate or not? So there's two numbers. One of them is run up, which means how high did the water get?
No, on inside the lake.
Yeah, that's called inundation.
Oh, sorry.
But it's another thing that you want to be able to
Yeah,
predict.
that's what I was
Yeah.
thinking.
Yeah.
So, but within these models, you cannot make estimation of inundation?
No, you can
or-
make estimations, but
Within these models, yes?
yeah, but their accuracy won't be very
So if you
good.
have shallow water on a slope, you can make an estimation of where the contact point goes, right? That's I think how they do it.
With all the debris is the
Yes.
unaffected, we have no idea what kind of
That's
dissipation.
right. So again, it's dissipation that's
Yeah,
the problem.
yeah,
Right.
that's what on land is there, is the trouble, we have no idea.
But if there's no dissipation, you can predict how far
Right,
things
right.
go up.
yeah. So it's easy to make a prediction. Whether you should bet any money on it is a separate issue. Yeah.
Harvey, regarding the dissipation, sorry, the dispersion, that issue was already addressed in the 60s, wasn't it? There was this guy from MIT who looked at the effect of dispersion on the linear equation, and you could see that it really affected the solution. I mean, you really got to.
So Sue and Gardner is another people who invented this equation, which is also called Green-Nagdi and also called Serre.
It was just linear theory. I mean, you can do the initial
Yeah, the
failure problem. and you-
dispersion, yeah, from all the models we're talking about now, it's just dispersion is is the main thing you're worried about,
Yeah.
and that comes from linear theory.
But that was surprising because they all thought it was really shallow water, whereas you could clearly see that big. But it's a problem of the fact that you have long propagation. Yeah, the small dispersion gets time to act.
Well, think about that second experiment from Joe Hammock.
Yeah.
That was not small dispersion, and there's an awful lot of energy in those short wavelengths. So,
So there should be an asymmetry if you push the block up, right? So then you get a more hydraulic-like jump, don't you?
which up is where you get solitons, if they have a long enough distance to go. So,
You're gonna get both.
pardon?
You're gonna get solitons in the tail, but the tail will.
Yeah, the tail will be small, it'll be behind all the solitons.
Just to be sure, right at the beginning, when you raise the block or drop the block, that's where you already generate the waves which disperse differently, right?
No, it's,
They appear emerge later from that.
it's,
But you need to do the dispersion right from the beginning, is that correct?
I don't think so,
You
actually.
don't, so you could start with shallow water and
I think
add it
you can
later.
take shallow water all the way till you're, I don't know, 200
And then
kilometers
later.
offshore, and then put it in locally.
Okay.
So I think what people really ought to do is if you live along the beach, do a model that's relevant for
And
your
then you
20
turn it on.
meters, and then do it several times so the wave can come in from here or here or here. But then you'll see what happens locally, and then you'll know what to do.
So, I had a couple statements about this dispersion. One, there are measurements of the Japan tsunami near off the Washington coast, which show the initial impact of the tsunami, which of course is much modulated from what it did in Japan, but then approximately 20-minute waves that go on for over 24 hours. And this is a dispersion for me, this is the other one, this is the elevation wave heading off
Mhm.
across the Pacific.
Mhm.
And the length of that signal, there's dispersion which is not in the operational models, which
Right.
are indeed shallow water.
Yep.
And I would be interested if, and those signals are on the web and you can get them, I'd be interested in a modeling of the upward wave and it. Also in the Sumatra incident, the waves hitting Sri Lanka or southern India, but Sri Lanka is more well tabulated. They were not necessarily, they varied whether they were first elevation or depression waves, but the eyewitnesses say there were like 7 crests at about 20-minute, half-hour intervals. And you used to at least be able to read about it on.
There's a guy named Chapman, who might have been from here, I don't remember where, but there's a geophysics guy who took his family to Sri Lanka, and they were vacationing in Sri Lanka, and at some hotel, and they watched the way they watched this water come in, and then will go back out in a fairly quick time relative to a tide, and he asked the guy who owned the hotel something, and the guy said blah 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 blah, and he said, no, that was a tsunami. Get everybody up to the second floor, and they did, and then
the next time it took the hotel first floor out.
Yeah.
I read this on the web. Yeah,
Yeah.
it's an amazing story.
yeah.
Just a small comment. So now satellite data for tsunami become available, and this dispersive tail is clearly visible and recognized. But the reasons why it was not taken into account earlier, that it's complicated the simulations, and the most people wanted is to know when the first wave will come, and details were anyway not reliable. And so at least when first people were starting to take dispersion into account, the results they were getting were worse because of the noise, numerical noise, and everything. So it took some time to improve numerics to use it the model, and still operational models are just shallow water, so that's they used in without dispersion. So that's yeah.
I have a last comment, which is the impact on the shoreline. Okay, very detailed, all the details around the shoreline, but it seems to me that there are a certain number of canonical models that could be used as at least as a starter for this impact, which I've seen. One is straight shoreline and straight sloping beach. Another one would be a convex shoreline. Another one would be a concave shoreline. Another one would be like the
Is this a hold? Oh, I can hold. I can hold it or put it in my.
Was sort of a linear focusing entrance shoreline. Something that will give us at least a first order approximation of what happens.
People do that.
Okay, well, that's a good time to transfer to the next speaker. Our next speaker, Professor Keelis with a very long first name.